So in this talk, we're interested in KB hypergraph.
It's not a good day.
Okay, good. Okay, so what are KB hypergraphs? So we have a vertex set, and we know the vertex, the number of vertices by n for most of the talk. And then there are these edges. Each edge is a subset of size k in a KB hypergraph. For example, here, it is KB hypergraph, each edge is a subset of size k. It's a generalization of graph. And what do we mean by chromatic number of hypergraph? So it's just a coloring of vertices with say c colors, so that no hyperedge is monochromatic. For example, if you look at this red and blue coloring of this hypergraph, if you look at every edge, it's not a monochromatic edge. You see a red and a blue color. Right? So it's a proper coloring of this hypergraph. And chromatic number of the hypergraph is the minimum number of colors that you need so that you can properly color the hypergraph. For example, this hypergraph is 2-colorable. So what do we know about the finding 2-coloring of k-uniform hypergraphs? Like in a graph case, if the graph is 2-colorable, it's a bipartite graph, and we know how to we know how to decide in polynomial time whether the graph is 2-colorable or not. But in case of k-uniform hypergraph, where k is at least 3, it's NP-complete. So we can't distinguish whether the hypergraph is 2-colorable or not in polynomial time unless p equals to NP. Right? So in this talk, we are interested in a relaxed goal. So what is the goal? We have given a graph, hypergraph, and suppose you know the guarantee that it's 2-colorable hypergraph. Okay? And we are interested in finding a proper C coloring of it for some larger C, for example 3, 10, log n, but it should be a proper C coloring of the hypergraph. Okay, so it's an easier goal than just finding a 2 coloring. For which values of C is this possible in polynomial time? This is the main interest of this talk. So at least is the question clear? And you can interpret questions anywhere in between the talk. The talk is very short actually. So what do we know about the algorithm, about known algorithms in this case? So this is the algorithm from 2001, which says that if we know that if we are given a hypergraph which is 2-colorable, then in polynomial time you can actually find a coloring which is non-trivial, but with how many colors? So the color which we require is n to the point 2. So of course finding a coloring with n colors is trivial. We just assign separate colors to each vertex, and this theorem says that you can do somewhat better than that. Okay, and we are interested in proving the opposite kind of result, which says that you cannot do something in polynomial time unless something happens. Okay. So why is this problem interesting? First of all, approximating hypergraph coloring is pretty much very closely related to PCPs. And in some sense, it motivated the formulation of unique gains conjecture, and since then, the problem received a lot of attention. And in answering this hardness of approximating hypergraph coloring, many new techniques were used, for example, split codes and short codes. These are just some objects which were used in giving better and better results in this area. So what is known about this problem? So don't get confused by this slide, so I'll just pass it slowly. So again, so I forgot to mention. So let's call the let's define the problem hypergraph 2K, which means that you have given a k-uniform hypergraph which is 2-colorable, and you are interested in finding C coloring of it. Okay, so this notation means that your given hypergraph is 2-colorable, and then you want the best C where you can do this in polynomial time, and C coloring in polynomial time.
Sorry, so for a fixed C, is it formally easier or harder as you increase K?
As you increase K, it should be easier. Right, because the monochromatic condition is relaxed. I mean, you have like every set of K vertices or hyperedges of size K, and there you just want that set is not monochromatic. But of course, it's incompatible in the sense that
Thomas is also weaker.
Yeah, the other side is also weaker. So in the sense, it's incomparable.
The There's no
So in
order.
fact, who is this result by? Somehow I thought the exponent there was tending to 1 with as k. It was something like 1 minus 1 over k. It's really 1/5?
Oh no,
all
it's
k?
1/5. Yeah, it's 1/5. If you don't have any guarantee, if you just know that it's 2-colorable, and yeah, then it's just 0.2, or maybe slightly better than 0.2, maybe 0.19 or something. But it's not tending to 1. It's
Just k grows.
as far as yeah. So what is known? So this slide is about the hardness of approximating hypergraph coloring. And the focus of this talk is 2-colorable 4 uniform hypergraph. That's why these rows are highlighted in green. So let me just first go over it. So the first result was by Hastad and Sudan. It says that given a 2-colorable 4 uniform hypergraph, you cannot color it with log-log n colors. Okay, unless their result was assuming that some conjecture like NP is not in quasi-polynomial time, but due to this result by Moshkovitz-Raz, which gave better PCPs, one can their result directly implies that this hardness result holds if you just assume P not equal to N. So it's the NP-hardness of approximating hypergraph log-log n colors. Then after more than a decade later, Saket improved this bound from log-log n to log n or polylog n, where delta is some constant between 0 and 1. Most probably it's very close to 0, some 0.0001. But the point was it improved this log-log n bound to polylog n bound, but it assumes that NP is not in d time n to the log-log n. And what this work shows is that if you just assume P not equals to NP, then we get a hardness of similar factor, polylog n. And if you assume this NP is not in quasi-polynomial time or NP is not in deterministic time n to the log-log n, then you get improved approximation factor in the sense that here the exponent was very small, 0.001, and here it's almost 1 minus 3 kilo 1. So the main point is that for hypergraph coloring, this improves the NP hardness from log-log n to polylog n, which is the exponential improvement the hardness factor. So is everything clear? And then and then you can study the problem for other uniformity and some other guarantees that the graph is say 3-colorable, 3 uniform, then what can you show, and all these things. And the long line of research is to improve this factor, whatever this log n or log-log n, polylog n. And the best known factor now is this 2 to the polylog n. Remember, in this algorithm, the factor was poly n, and we are just trying to reach this poly n factor in from the hardness side. Okay, and then so if you increase the uniformity, then proving hardness result is easier and easier. So maybe can you show that given a 2-colorable 100 uniform hypergraph, you can't color it with say poly n colors? That would be nice to show. And in this respect, this is the result by both and Saket and Verma, which shows that given a 2-colorable 8 uniform hypergraph, where the uniformity is 8, you can't color it with 2 to the polylog n colors. Almost approaching the log n bound, almost approaching the poly n bound. So yeah, so like I said, the main results is one is that if you just assume P not equals to NP, then you cannot color a 2-colorable 4 uniform hypergraph with polylog n colors. And if you assume this non-standard assumption, then you cannot find the coloring with almost log n colors in polynomial time. So I'll just give you the proof outline, and hopefully, since the proof is very short, I'll go over the whole proof and hopefully try to convince you with each and every part of it. Okay, so how does the reduction, any reduction looks like? It looks like you start with the 3-side instance, and then you reduce it to, in our case, you reduce it to a 4 uniform hypergraph. Okay? And then you want 2 guarantees to hold. If the 3-side instance is satisfiable, you want your hypergraph to be 2-colorable, and if it is not satisfiable, you want your hypergraph to be not c-colorable. This will show that the distinction between 2-colorability versus c-colorability is NP-hard. But luckily, of course, we don't have to start from 3-side. We have this much sort of harder problem, not really, but we have this very large, very nice problem from where we can reduce it to our hypergraph. So let me define the hard problem first. So the problem is called label cover. So what is it? You have given a bipartite graph, okay, and there are these edges between these two parts, and there are these labels. So labels R and L. Think of R as say 1 million and L say 1000 or something. And each edge is labeled by a projection from L to R. Okay, it's just a function from L to R, but more precisely it's a projection. And what is the goal? The goal is to assign labels from L to these vertices and labels from R to these vertices so that it satisfies as many edges as possible. Okay, so what do we mean by satisfying an edge? If you look at this edge, the projection is given by the function phi e1, and if we label this vertex alpha and this label this vertex beta, then we say that these labels satisfy this edge if this holds. That with respect to phi e1, alpha gets projected to beta. And so the goal is just to find the labeling to these vertices so as to satisfy as many edges as possible. Okay, so what is known about approximating, or what is known about how efficiently can we solve this problem? So let's define the problem gap LC 1 and epsilon, which just asks distinguish between these two cases. One is that there exists a labeling to these vertices that satisfies all the constraints, so it's perfectly satisfiable label cover, versus no assignment can satisfy more than epsilon fraction of the constraints. So think of epsilon as 0.1, 0.001, or you can think of epsilon as even sub-constant with respect to the size of the graph. So here the task is just distinguishing between satisfiable versus say satisfying some 0.001 fraction of the constraints. And there is a theorem, so this theorem follows from parallel repetition, PCP theorem and parallel repetition by Raz, which says that for all constant epsilon, gap LC 1 epsilon is NP-hard. So yeah, for any constant epsilon, no matter how small it is, if it is a constant, then distinguishing between these two things, satisfiable versus epsilon fraction satisfiability is NP-hard. And since in our reduction we would need epsilon to be sub-constant, we will use somewhat more efficient reduction, which was given by Moshkovitz-Raz. So what this reduction shows that it reduces a 3-sat of size n through this gap LC, but the reduction runs in time, so the exponent of n is independent of epsilon here. So it's not very important, but the point is that for our efficient reduction, we will need this theorem, and I'll come back to this later why we needed this efficient reduction. Because in this reduction, the exponent of n will be 1 over poly epsilon, and here it will be just some constant independent of epsilon. And the label size produced by this reduction is exponentially 1 over poly epsilon. So again, I mean, I'll come back to this later. It just shows that for sub-constant epsilon, you can have this label cover where the reduction runs in polynomial time. Whereas it did not follow from this theorem. Okay, and although we are using this theorem as a starting point, one can basically use label cover for people who know who are familiar with PCBs. One can just use label cover which is derived from low degree tests, which is like you don't need all this. This is a very complicated paper, so you don't need all this complicated theorem. You can just derive it from label cover, which you get out of low degree test, which now these days they have a simple also. Yeah. Okay, so how does a typical reduction looks like in this sort of area? Starting from a label cover. So you start with label cover with some gap, and then you replace this vertex, each vertex with some cloud of vertices of size say 2 to the L. There is just one very informal way of describing how the reduction goes if you start from label cover. Okay. So you replace each vertex by some cloud of size say to the L. Okay. Maybe you can represent each node here by a string of length L, binary string of length L, and these will be the vertices of our hypergraph. Okay, and somehow you put hyperedges amongst these vertices. Okay, so if you start with label cover here, the number of vertices you produce is size of u times 2 to the L, and somehow you put some hyperedges across these vertices. And of course, like I said, we need two guarantees now to show hardness result. One is that if the label cover instance is satisfiable, then your hypergraph is 2-colorable. And second is that if the hypergraph is c-colorable for some large c, then you can recover epsilon satisfying assignment for the label cover. This will show the gap of 2 colorability versus c-colorability. But yeah, so the problem with these kind of reductions is that so this is not very formal, but to get a large gap between 2 and c, remember our goal is to prove something where c is as large as possible, maybe hopefully poly n. Okay, but to get a large gap, we will need very small epsilon in this reduction. But epsilon should be at least 1 over L, because if the labels are L and R, just a random labeling satisfies 1 over L fraction of the constraints. Okay, so epsilon better be at least 1 over L. If we say that the gap LC 1 epsilon is hard, which means L is large, but then where is the size of L is coming into picture? In the sense, it is coming there because the size of the hypergraph that we produce is of size of u times 2 to the L, and this is too big for the reduction, for our NP hardness reduction. Right? So what we do is, instead of using all these 2 to the L vertices, we will restrict to some small subset of the vertices, and that's how we will get some efficient reduction and show hardness based on just polynomials. Okay, so what objects do we use? Are we using instead of this? So these are the vertices of a graph called Schreiber graph. Okay. So let me define what the Schreiber graph is. It is indexed by 2 parameters n and L. Okay. So the vertices are all independent sets of size L in this cycle graph Cn. And 2 vertices are connected, which is just a subset of 1 to n, if they are disjoint. So in other words, if you represent vertex as a string of length n, so each vertex is a binary string of length n, but not every binary string of length n constitutes a vertex. So it should be an independent set of size L in Cn, right? So the Hamming weight should better be L, and then there is no 1 1 consecutive 1 1 here. If we just use the indicator function or indicator vector of the independent set. So possibly this represents a vertex in a Schreiber graph. And 2 vertices are connected if they are disjoint. So if you just put 2 vertices here, then we want that in every coordinate you don't see 1 1. That's just saying that you connect 2 vertices if the independent sets corresponding to the 2 vertices, they are disjoint. So this is so why is it interesting? So first of all, the number of vertices in the Schreiber graph is too small. It just at most n choose 2t. This is just simple counting. So instead of 2 to the n, we have the number of vertices which is just n choose 2t. This is important. And the second most non-trivial fact is that the chromatic number of this hypergraph is 2t plus 2. So now I am switching. So I am replacing these parameters n and L by replacing L by something like n over 2 minus t. So the Hamming weight of every vertex is almost half n over 2. Okay. And if you look at Schreiber graph with these parameters, the number of vertices is very small. And the chromatic number of this Schreiber graph is 2t plus 2. So this is a very highly non-trivial fact. Although the graph and its description looks very nice and simple, but proving the exact chromatic number of this graph, actually the only proof known is topological proof. It does not have any combinatorial or simple elementary proof. So that might be. Okay, and we will need both these facts for our data. So any questions so far? Okay, so how do we, so we start with label coinstance. So this is our label coinstance, and we replace each vertex with a Schreiber graph, with a copy of Schreiber graph, where the parameter is Schreiber graph, where n is L, and the parameter L is L over 2 minus t for some parameter t. Okay. The point is that the number of vertices here should be much smaller than 2 to the L, and we will set these parameters accordingly. So we are replacing each vertex by a copy of Schreiber graph. Okay, and these will be the, so you can think of each node here as just a string of length L, but of course it should satisfy this property. There are no consecutive ones. And these will be the vertices of our hypergraph. Okay, so what we gained is that the size of our hypergraph is just n times 2 to the 2t log L. Instead of 2 to the L, we get exponential improvement in the size of the hypergraph. Of course, I haven't defined you what the hypergraph is, but just the number of vertices is too few. And now, like I said, we'll define hypergraph by selecting 2 vertices from here and 2 vertices from here carefully. So let me go over it. So now consider 2 clouds corresponding to vertex u and w, okay, which share a common neighbor u. Okay, for every such pair of clouds, we will put hyperedges between 2 nodes here and 2 nodes here. So let's see the condition which we require for this A, B, and C, D to form a hyperedge in our hypergraph. So let's write down A and B and C and D in the binary in this format. Okay. Since the first condition we require is that AB is an edge in this Schreiber graph. Also CD is an edge in this Schreiber graph. Okay. What does that mean? It means that there is no 1 1 in any of these coordinates. Similarly, there is no 1 1 in any of these coordinates. Right? Because the adjacency is when the independent sets are disjoint. Okay, so that's one condition which is satisfied by A, B, C, D. And the second condition that we need is that just highlight all the coordinates where you see 0, 0. Okay, suppose in AB, these are the coordinates where you see 0, 0. In CD, these are the coordinates where you see 0, 0. Since we are looking at Schreiber graph with these parameters, first of all, the number of coordinates is too few. It is at most, say, I think it is at most 2t, because each string is of Hamming weight L over 2 minus t, and this the locations of ones of these and these are disjoint. Okay, so one observation is that this set is small. So we put an hyperedge between A, B, C, D if it satisfies this property. Okay, what is this property? Look at any coordinate I where you see 0, 0 here, and any coordinate j where you see 0, 0 here. You want that they do not project to the same coordinate with respect to this projection pi u and pi e. For every such coordinate here and here, you want this condition to go. And we will see in the next slide why we require this thing. It will be clear why we need. So let's put that condition over here. And these are the picture of when we put hypergraph in A, B, and C. Okay. So this completes the description of the hypergraph. Okay, so what we did again is replace each vertex by a copy of the hypergraph, and a hyperedge between 2 vertices from here and 2 vertices from here, we satisfied all these properties. So now we need to show two things. One is that if the label coinstance is satisfiable, then the hypergraph we constructed is in fact 2-colorable. And if the hypergraph is say polylog, if you can color the hypergraph is say polylog n colors, then in fact you can recover good labeling for the label for instance. Okay, and these are called completeness and soundness. So let's see the first, the easy claim that if the label for instance is satisfiable, then it is 2-colorable. Okay, so we need to come up with coloring of these vertices with say 0 and 1, which does not lead to any monochromatic hypergraph. So yeah, I mean, so let's start with the assumption. The label, for instance, is satisfiable. Okay, so let's fix the satisfying assignment. So this assignment, this labeling L labels these vertices from L, and these vertices, these vertices from L, and these vertices from the labels 1 to R. And now to color a vertex A from the cloud of V, so A is a string of length n, finite string of length n. From cloud V, you just color it with A subscript L of V. Right? We just go to the location L of V, which is a number from 1 to L, and just output what you see in that location. Right? So it's a 2-coloring of the hypergraph, but is it a proper 2-coloring? So the proof is that it's a valid 2-coloring is the proof by picture. So let's say, suppose you have an edge A, B, C, D, and the satisfying labeling labels this vertex alpha and this vertex beta. What we are showing is that we are assigning AB with 0, 0 and CD with 1, 0. That's what this labeling, this coloring is saying. Okay. So if alpha and beta are such that it happens that it's not monochromatic, then we are good. I mean, at least this hyper edge is not monochromatic. The only way it can be monochromatic is if it satisfies this thing. That you see 0, 0 at the alpha location here, and you see 0, 0 in the beta location here. Right. But why is this not possible? Why can't you have label alpha to this vertex and beta to this vertex, so that you see all 0, 0? Yes?
Because then I of B1 would equal, I of B1 of alpha would equal pi of B.
Precisely, yes. Because this is a satisfying assignment, these two labels should project to the same label over here. Okay? And so alpha and beta are projecting to the same label over here, but then remember the condition that we use while putting a hyperedge between A, B, C, D. That whenever they project, so whenever you see 0, 0 and 0, 0 in here, they should not project to the same element. So this cannot be the case. You won't have a hyperedge between A, B and C, D if this was the case. So this is a valid 2-coloring, so at least the completeness case is fine.
You get an even stronger condition in this case, like for every hyperedge, where it could have like any number of reds and blues between 0 and 4. Like
Yes, you can.
it has
In
like
fact,
only 0, 1, or 2 reds in every.
right, you can have that condition. Either it's you can't have 3 1s and 1 0,
Or 4 ones.
or 4 1s will be monochromatic, right?
Oh yeah. Okay.
So yeah, in fact, so valid 2-coloring of 4 uniform hypergraph can mean that there is 1 1 instead in 4 vertices, or 2 or 3. But this in fact shows somewhat stronger in the sense that in a valid 2-coloring you don't see 3 1s in any hyperredge. So the completeness part is fine. Let's move to the soundness part, which is the trickier part in most of the cases. So the claim is that if the hypergraph is somewhat efficiently colorable, say with 2t plus 1 colors, okay, then the label cover is 1 over t cube satisfiable. Okay, think of t as small. If t is small, then we are in fact finding a labeling which satisfies many constraints from the label cover. So this is what we need for the reduction to work. And I just set up the parameters so that it works. So let's see. So fix the 2t plus 1 coloring of our hypergraph. Remember, these are the vertices of our hypergraph. Now, in every cloud was a copy of a Schreiber graph, right? And what we know is that the chromatic number of Schreiber graph is 2t plus 2 with these parameters L and L over 2 minus t. So in every cloud, you will see at least one monochromatic edge. This edge is from the Schreiber graph, or the Schreiber graph edge. Okay, so in every cloud you will see one edge, monochromatic edge. Okay, and by averaging you can say that there exists a color green, so that monochromatic green edge is present in most of the clouds. Say 1 over t fraction of the clouds will contain 1 over 2t plus 1 fraction of the clouds will contain monochromatic green edge. This is just by averaging. Okay, and just label these vertices, just focus on these vertices now, where you have monochromatic green edge. Now, what can we say about AB and CD? So, suppose the monochromatic edge in this cloud was AB, and the monochromatic edge in this cloud was CD. Of course, they share a common variable. They have a constraint with a common variable. What can we say about AB and CD? So, let's write down AB and CD. Okay, so A is some unnesting, B is some unnesting, C and D, and they have. So this is an edge from the Schreiber graph. So there is no 1, 1 in any coordinate, because it's an edge in the Schreiber graph. The independent sets are destroyed. Okay, you will see 0, 0 in some locations. At most, say 2D locations, you will see 0, 0. Okay, and similar is the case with C and D. You will see 0, 0 in few locations. At most 2D locations. So the claim is that there must exist I and j from this 0, 0 location. So there must exist a coordinate I where both A and B are 0, and a coordinate j where both C and D are 0, such that they project to the same level with respect to projection phi 1 and phi 2. This is the claim that we want to show. So what we did is that we separated out this edge A, B and C, D, and we are just focusing on the 0th location here. And what we are saying is that there must exist a common coordinate, or there must exist a coordinate I and j, which projects down to the same same level with respect to these projection constraints. Okay, why is this the case? Suppose not. Okay, suppose for every I and j like this, they don't satisfy this property. But what does that mean? Yeah, it's a hyperedge, right? Because this satisfies, if for every I and j, this condition does not hold, then this is a hyperedge, because this was precisely the condition we wanted for A, B and C, D to form a hyperedge. And if this condition does not hold for any I and j, then this is a contradiction, because we found a monochromatic green hyperedge in our polynomial hypergraph. Okay, so this must be the case that there exists I and j where they project to the same coordinate. And we are done. So let's call this subset of 1 to n where you see 0, 0 in AB as say SV. So what we found is that for every green vertex here, you found a subset SV of size 2t. But what property it has? So this is a subset of L, and this is a subset of L, and both they are of small size, because it's just the it's just the locations where you see 0, 0, which was at most 2t, because this was the edge in your Schreiber graph. And what we know is that if there is a common vertex here, there is so let's project all the labels SV with respect to this projection. Okay, there are at most 2t labels here, or exactly 2t labels here. Let's project on all the labels here. You will see some subset of size 2t, at most 2t, from some subset of R of size at most 2t, because we are projecting only 2t labels. Similarly, this will give you some subset of size 2t. And what this condition says that these subset must intersect, because there must be a coordinate here and here which project to the same element. So if you look at all these projections which is coming from the neighboring set of U, then all these are pairwise intersecting. It is clear because in every pair there is a coordinate which projects to the same element. And this gives you efficient labeling. So how do you label U? You just pick a coordinate K from R, which is the most common in all these subsets. So the claim is that if S is a family of subsets which are parallel intersecting, actually if we have family of where each subset is of size K and pairwise intersecting, then there exists R from N which is present in one over K fraction of S. So this is a very simple claim to prove. You have a family. What does that mean? That for 1 over T fraction of these edges, there is a label here which projects to this particular K. Okay. So this will give a labeling for these vertices, for this right hand side vertices, and for left hand side vertices you just select a random label from SV. Remember you had these small sets of size 2D. For these things you just pick a random label from SV. And then it's not hard to show that it satisfies 1 over TQ fraction of the labels from the label cover instance. And here we are using some biregularity of the label cover instance in the sense that we already zoomed into these vertices where the green monochromatic edge is present, and we showed that it is 1 over T fraction of the vertices. And what we are showing is that we are just satisfying constraints between the green vertices and this right hand side. Okay, but because of biregularity you have enough constraints there, and from that set you are satisfying 1 over T fraction of it. So overall it satisfies 1 over T cube fraction of the constraints. Okay, and this finishes the proof. Okay. And so let's set the parameters. So now let's recall. So the size of the hypergraph was U times L choose 2T. These are the number of vertices of Schreiber graph, which is n times 2 to the T log L. Okay, and we start with the gap level cover, where epsilon we take is 1 over polylog n for very small delta prime. Okay. And the label set produced by the Moshkovitz-Raz reduction, this I said I'll come back later, is exponentially in 1 over poly epsilon. So which is just So if you just plug it here, the size of the hypergraph you get is n times 2 to the polylog n. If you set T to be log polylog n. So this T is polylog n, whereas this is much smaller than 1. And log n is just log to the delta prime n. So the overall, the number of vertices is just in fact almost linear in n. And of course, we got the gap that the hypergraph is not 2T plus 1 colorable in the soundness case, and T here is log n. So the number of vertices was almost n, and what we are showing is that you cannot color it with log to the delta n colors in polynomial time. So this finishes the paper. Any questions? Okay, so there are two important questions. One from the algorithmic side is, can we improve this n to the 1 over 5? Can you prove better algorithm for this coloring hypergraph? And of course, can you improve this polylog n bound? Since there is a gap between polylog n and poly n, can you improve the gap from the hardness side? Even a q-colorable k-uniform hypergraph, can you show that it cannot be colored with better than polylog n in polynomial time, assuming P not equals to. Yes.
Why is there a uniformity condition?
Why is
Because
there?
like if you say there's 3 uniform,
Mhm.
why not just allow 2 and 3?
Yeah, you can allow 2 and 3, and there also it's interesting. Yes.
I mean, isn't it trivially, is there any reason to put the uniformity statement as possible?
No, I mean,
I think K-uniform hypergraphs are popular.
Oh,
Prominent orders.
because it's popular, okay.
yeah, but I mean, it will be interesting if you put
And
3,
most-
4, 5 uniform. I mean, if you consider all these different uniformities, I think the problem will still be as difficult as doing it for just K uniform hypergraphs.
I mean, it's a special case, right? K uniform is a special case of up to K, and you're proving hardness.
Yeah, but then in that case, yeah, I think if, okay, maybe if the proof works for say uniformity 3, 4, 5, it should work for uniformity 3, I guess. Yes.
And just to clarify, so you gave 2 results, one assuming P not equal NP and one
Yes.
assuming the stronger hypothesis. Is the only difference just how you set the delta?
Yeah, exactly. So for the other result, you use the label cover given by the Raz's parallel repetition and PCP theorem, and you just set the parameters. So the reduction is exactly the same. It's just this slide which is different. So the advantage of the other reduction is that so there are these 2 reductions, right? This produces a label set of size exponentially in 1 over poly epsilon, whereas this produces label sets of size just 1 over poly epsilon. So the advantage of this reduction is that. So if you just plug in the parameters, then you get the log n over log n bound. But of course, as soon as the epsilon is sub-constant, this reduction does not run in polynomial time because there is some 1 over epsilon here. So, but the reduction is exactly the same, just setting the parameters.
So is there a relationship between this and, say, the hardness of, you're given a graph that's 3-colorable and you want to color it with a few colors.
Yes.
Is there a relationship between that sort of hardness and this sort of hardness?
Yeah, so there is no direct relation. So I guess there is no direct relation between hardness of these kinds and that kind. For graphs, the problem is much more difficult from the hardness side. So given a 3-colorable graph, can you color it with say 6 colors? I think this is still not known. Even if you assume sub-exponential time, I guess, quasi-polynomial time, polynomial time.
And you color it in what, n to the 1 over?
Yeah, I mean for 3-colorable graphs, I think this is a result by Aurora and Ronga, which shows that you can color it with some n to the 0 point. I don't remember whether it's less than 1 over 5 or greater than, but it's
now
some.
it's less than 1 over 5.
Is it?
Kawabayashi Toru beat.
Oh, I see. Oh,
Into
I
the
see.
point 1999.
Oh, this is the later result.
Last.
I see. So in that case, you can color it with 0.199. But still, it's still polynomial. There is still huge gap between hardness and algorithms. Yes.
So here you focus on the hardness results. So you said that, okay, coloring a hypergraph is hard even if you assume that it's 2-colorable.
Yes.
So is that because, like, assuming that the hypergraph is 2-colorable isn't that useful of an information? Is that why, or where is the, or like,
Yeah. I
could
mean,
you replace it by, like, I'm trying to see what's causing the hardness. Like, even if you're assuming that it's 2-colorable, it seems like the problem's still hard.
right.
So what is causing this hardness? It's more of a high-level question.
I don't know. I mean, the same reason as why 3-colorable graphs cannot be 3-colored, or why is it NP-hard to find a 3-coloring?
So it's just not that useful of an information. Tell me that's. Can you replace it by another condition where then like coloring would become easier, at least in the approximate setting?
maybe we could say k-partite, then it's
Yeah, I mean, suppose you have given a graph which is k-partite, hypergraph which is k-partite. Okay, then can you find true coloring of it? You can ask this question. But in that case, it's possible.
I see.
So given a k-partite hypergraph, you can find a true coloring. Still, it's not known whether you can find say 3-partite of the k-partite. I mean, three partitions, or in fact k partitions. It's not known. The only thing known is that given a k-partite hypergraph, you can color it with 2 colors.
So given a k-partite 2-colorable hypergraph.
Yeah, k-partite is always 2-colorable.
I see.
Right, because there are k parts so that every hypergraph goes like this. So there it's possible to 2-color it, but it has a very strong structure. And you can ask, I mean, if you just relax the structure a little bit, can you do 2-coloring? For example, if it is k-1 partite, can you 2-color it? I think it's not.
So for hypergraph, I guess the other way to there's also like the rainbow coloring sort of.
Yes, so this, yeah.
Yeah, and I'm wondering, are there similar sort of trade-offs? Like say I give you like a 2K rainbow colorable uniform hypergraph, is it still hard to be like?
Yeah, so for example, partiteness is precisely the rainbow coloring, right? So
Oh, it's exactly.
if it is a t-partite,
Oh,
then
okay,
it is
yeah.
t-rainbow coloring.
Oh, I see. I see, yeah.
Yeah. So you can study that one too. And there also very little is known for some parameters.
We had some, so I think with Venkat we had some results that like if the graph is t rainbow colorable or something, then you can color like n over t to the t, 1 minus 1 over t to the t fraction of edges or something like that.
Oh, I see. So this is from the algorithmic side, but
Yeah.
you don't want to satisfy all the hyperedges. You want to maximize the fraction of hyperedges.
Right, fractional satisfiedness. And like for minimizing the number of colors, it was like n to the some function of t, I can't remember it was.
Yeah, from the algorithmic side, even if you assume the some k-1 rainbow colorability, the best known algorithm is by Venkat and with you also. This is the recent thing.
Yeah, it was like 3-4 years ago.
Oh, okay. Yeah. So which also colors it with n to the epsilon colors. There also from the upper bound side the bound is polynomial in there. And from the hardness side nothing is known, not even 2.